Good day, good evening, and welcome to today's webinar. My name is Mark Cox. I'm a senior communicator at INNIO Jenbacher, and I'll be your host today. The Jenbacher North American team is presenting a series of webinars this fall focused on topics such as combined heat and power, microgrid solutions, hydrogen for data centers, food and beverage, wastewater, green and grow houses, and more. Please visit www.jenbacher.com/America for more information on our webinar series for North America and register today. It is my pleasure to welcome you to this webinar titled CHP for Commercial Buildings. Today's webinar will run for approximately 1 hour, including about 15 minutes for question and answers. You'll notice that this webinar is browser-based, so if you disconnect for any reason, please just click on the link that you received via email to rejoin the session. We want to make sure that this webinar answers all of your questions about CHP. So in order to ask questions, you can send them in via the Questions widget. Just type them into the box at the top left-hand corner of your screen and click Submit. Please use the yellow Help widget if you require any assistance, and you can move, resize, and maximize any of the windows in front of you to get a better view of the slides. There is also a short series of questions available under the Survey widget. We'd appreciate if you would take a moment to give us feedback on today's webinar. INNIO is a technology company developing, manufacturing, monitoring, and servicing gas engines for power generation and compression solutions. Our Jenbacher products are specialized in power generation. With more than 1,000 gas engines delivered in the U.S. and Canada, Jenbacher is a key player in the transition to cleaner, more efficient energy in North America. Our North American operations are based in Houston, Waukesha, Wisconsin, and Welland, Ontario, in Canada. Jenbacher has been active in the North American market since 1993, and our expertise in gas engine power generation stretches back to the 1950s. In addition to sales and manufacturing, our North American footprint includes a network of life cycle support teams, which help our customers avoid costly downtime, extend the lifetime of their engines with our remanufacturing programs, including local warehouses for spare parts, and provide real-time monitoring with our myPlant asset performance management tool across 50 industries. With Jenbacher gas engines, power generation customers in North America receive top efficiency and performance, durability and reliability, a variety of applications to choose from, fuel flexibility, and environmental benefits. With that, I would like to introduce our speakers for today, Gary Farmer and Christian Mueller, both Senior Sales Managers from Jenbacher North America. Gentlemen?
Thank you, Mark. This is, everybody, this is Gary Farmer. As Mark said, I'm the Senior Sales Manager for North America, new units, and I'm located in the Baltimore-Washington corridor on the Atlantic coast.
And hello also from myself, Christian Mueller. I'm also a Senior Sales Manager for the Jenbacher product line. I'm based out of Houston, Texas. And I'm going to kick off the webinar here. So the topic of today is CHP for commercial buildings. And as a little introduction on our goals here of the webinar, and also our goals in terms of supporting you, both as end users as well as developers, EPCs, and consultants, is really to help you, if you're an end user, to analyze your energy data, which you have from your site, to do a pre-feasibility study if CHP makes sense for your operation, help you out with case studies where we've looked at similar applications like what you're trying to achieve, and to really help you justify your project internally so that it can move to the next step. If you're a developer, EPC, or consultant, we can provide you definitely the latest performance info on our products. We can give you cost estimates both for the equipment as well as the services of the units. We can provide you lessons learned and insights from past projects, as well as help you win more business by teaming up early in the process. As we all know, that's the key to getting in early on a project. As far as our agenda goes today, we want to cover a little bit on what CHP is. I'm aware probably many of you do know, but it's always good to have a little recap on that. We want to show you where CHP is used and why we do it. The Then Gary is going to talk about the economics of CHP, a couple case studies, as well as the process steps, followed at the end with questions and answers. So again, during the presentation here, if you have any questions, just put it in the team chat, and we'll get to hopefully all the questions at the end of the presentation. If not, we'll answer them after that in written form. So the definition of CHP, which is also known as combined heat and power or cogeneration, is that it's the concurrent production of electricity or mechanical power and useful thermal energy, which could be heating or cooling from a single source of energy, in this case, a gas engine generator. So it's really about combining different energy outputs here, electricity, thermal uses, which you can make use at your site. How does that look in a very simplistic form? You would have a gas engine generator here, as shown with the green Jenbacher engine. You would have fuel input going in, natural gas, biogas, any variety of different gaseous fuels that would be converted to electrical energy here on the bottom in yellow. And then there's two sources of thermal output from an engine. One would be the exhaust, which goes out to the top, which can be used to make hot water or steam, or from the engine jacket water, the cooling circuit of the engine, you could also recover that heat. And if you combine both of those sources from the engine coolant circuit as well as from the exhaust, you get a very high total energy recovered in thermal energy and can make use of that in your facility. Just as a rough number, if you look at an engine generator scope with the heat exchangers, that's probably about 35%. Oh, the slide went too far. Seems like it's moving on its own. Wait, sorry about that. Seems the slide deck is having a little problem here. Just going to scroll back here. Sorry about that. So hopefully the slides will now stay. Okay, well, sorry about that. What I wanted to say here, the CHP scope here, the gas engine generator with the heat exchangers, is about 35% of the total scope, so that you get some idea in terms of the capital cost of a project. Now we want to talk a little bit about where CHP is used in real-world applications. So this little diagram of an island here shows a bunch of different varieties where gas engine CHP systems could be used. Starting off from the top, that could be utilities and industrial power plants, sometimes only producing electricity, but if they have a large thermal offtake, they could also use CHP. Then going clockwise around the dial here, we could have organic processing facilities which might gasify organic waste, and you could have wood gas or syngas or other special gases which could be used in gas engines. Then a primary application is hospitals, universities, airports, municipal buildings. We definitely have a lot of those applications where we have CHP systems installed because they're a good fit. They are 24/7 applications running continuously where cogeneration makes a lot of sense. Then there are agricultural and food and beverage type users, which might actually have biogas from their treatment of, let's say, wastewater from the processes there, where they could also be using natural gas. And then obviously they have a large amount of electric and thermal needs there for that process they're having. Greenhouses are also a good application. So not only do they need electricity as well as heat, but they can also make use of the CO2 of the exhaust. Then we have landfills and wastewater treatment plants. They produce obviously biogas, sewage gas, landfill gas, and those can also be burned in a gas engine. Coal mines have also been an application where we put these units. Coal mine gas is a waste gas from coal mines, which needs to be discharged and can be burned in an engine to turn that into electricity. And lastly, oil and gas applications such as oil field and refinery applications, where also a lot of waste gases potentially are available to be burnt in an engine. So there's really a lot of different uses of gas engines, some with and some without thermal needs. But generally speaking, cogeneration type applications, if you do recover heat, make most sense where you have that continuous use of electricity and thermal, because then you get your best use out of it. As far as CHP sites in the US, it's definitely not a new technology. There are many different commercial sites. This is from the DOE, all those blue dots. Some of them with engines, some of them with turbines or other applications. But it's widely used, and 72% of the fuel used in those applications is natural gas. The top segments are really on the commercial side, universities, hospitals, and district energy sites. So there's definitely already a lot of CHP being used, and that's continuously expanding. So now I'll pass it to Gary to talk a little bit about why we do CHP.
Thank you, Christian. Just as a reminder, if you have questions, be sure to write them in the on the widget. And if you're having issues with the presentation, seeing it, or if it's freezing or anything, go back and refresh your browser. That should correct the issue. So, why do we have interest in CHP? First, let's look at CHP and compare it to the traditional central power plant type of system that we're familiar with, and it has been really throughout the country. It has been the norm throughout the U.S. for at least 1 century. So on the left side, shown in blue, is the separate heat and power. This would be the typical central power plant. In this case, don't worry too much about the kilowatt data and so forth. The important thing is the efficiency, the percentages shown on this particular chart. So with the central power plant model, to get the electricity out, it's roughly 36% efficient, which means you're losing 64% of the efficiency of the energy that's costing to produce that power. On the thermal side, you're getting 90% efficiency to produce the thermal energy, and you're losing 10%. The result of that is basically an energy loss of 49%, yielding an energy efficiency of that traditional model of 51%. So roughly you're losing half of the power, half of the energy that the fuel possessed before it gets to you, and that's the central power plant, as likewise with the transmission lines, step-down transformers, distribution lines, etc. There's losses on every step of that chain. Now, let's switch over to the right side, where we're looking at combined heat and power in green. For comparable sizes of power, we're looking at a 46% efficiency for the electricity produced, and 43% for the thermal energy produced. So we're getting a total loss of approximately 11%, which is netting us an energy efficiency of 89%. So you compare that to the 51% for the traditional central power plant based model, and it's a considerable difference. This is really the big advantage to CHP from the efficiency perspective. It's just huge. Moving on to a couple of the other things, distributed power. CHP, a lot of it is we're moving it closer to the source, so we're not running into these transmission and distribution losses that I mentioned on the previous slide. The economic, really the cost of this, I'm going to go through these 4 items. The cost, cheaper energy, that's the economic driver for it. So if the energy is costing a lot less to the consumer, obviously that's going to be very interesting, very interested in that. Number 2, the resiliency. Costly natural disasters. We've seen an increase in natural disasters over the last few years, blackouts, brownouts. We're going to go through some of those issues a little bit later on. But really what is this? What this is doing is running down the resiliency of the traditional energy model, which is making it a bit more conducive to CHP's applications. Number 3 is the clean and reliable power. We're showing a data center in this case, and obviously a lot of these critical facilities need clean, reliable power. In fact, one of our later webinars is going to be specific to critical power facilities. And this is, again, at the top, you're seeing that this is really driving sustainability. Again, another real driver for CHP. And last is slow grid interconnections. We're showing the traditional electrical utility grid here. And I particularly like the quote at the bottom: the pain cannot wait 18 months for utility power. For those of us who have experienced interconnecting to the electrical grid, it can be very lengthy and very expensive to do. And I'll go into that a little bit later on when we talk about the economics of CHP. Utility and energy trends encouraging CHP. On the left, you're seeing a quick chart with figures from 2007 through 2016, showing the average cost of the U.S. for natural gas and electricity. Electricity being the lighter colored curve at the top, and the natural gas pricing being the larger one at the bottom. And you see what's clearly labeled as gap. This is the difference between what electricity can be purchased for and what, excuse me, and what the natural gas can be purchased for, and what it can be produced at. And we'll go into that a little bit later in a little bit more detail. The insights into this really are really driven by the natural gas pricing dropping 65% over this time period. Meanwhile, industrial electricity prices had climbed 8%. So there is quite a bit of difference. Years ago, this gap was much narrower, and it was interesting in that sometimes it was quite difficult to justify CHP facilities from an economic perspective. And I'll touch on that a little bit on a later slide. The industrial trend is upward due to transmission and distribution investments and increased renewables. And just moving down a little bit farther, and CHP really allows customers to significantly reduce their operational costs from what they were doing before. Resiliency to drive more CHP. We're going to show two examples. The first is Superstorm Sandy. For those of you on the East Coast, you experienced it. For those of you on the West Coast, you probably just read you heard about it in the news. But as you can see in the photo, there's the Manhattan, the city that never sleeps, awfully dark due to power outages from Superstorm Sandy. On the chart on the right, you see these red squares from National Grid, and the other kind of a blue asterisk-looking crosshatch item with from Rochester Gas and Electric, one of the specific utilities. But you can see the frequency of outages was considerably less with these distributed energy systems. And you can see at the bottom too the little quote: among the sites where CHP unit was designed to operate during the grid outage, all of the CHP systems did perform as expected during Sandy. There was not a single site that lost grid power. And this was a survey done by NYSERDA about CHP sites. So that's a pretty good endorsement there. Another example is the Hurricane Harvey. This was in Texas, where the ERCOT grid exists. And actually, I should say in one of our upcoming webinars, I think pretty sure it's the one on microgrids. We're actually going to share some information about last winter's issues in the ERCOT market also. So anyway, so ERCOT in this particular case, as a result of Hurricane Harvey, had over 10 gigawatts of power down due to T&D lines. We're down, as you can see in the photo there. Those lines are dropping into the water, and it's going to be quite a bit to resurrect those lines and get them back upright and functioning. So the result of that was about 330,000 people, our customers, were without electricity, lingering storm and flooding, so excessive wait times for recovery. And then on the right, you can see some of the charts showing the electric load on an hourly basis during the Hurricane Harvey. Moving over into the environmental part, this is really a snapshot from a program we have using one of our model J624 gensets in a CHP application. And it shows the environmental impact by using this engine, offsetting all of the blocks that you see below it, both in greenhouse gases, and then in the lower line or lower row is the carbon sequestered by using the J624. So it's pretty significant. I won't go through all these. You'll be able to see these later online when you can take another look at this presentation at your leisure. Moving on with emissions, this chart shows the greenhouse gas improvement for CO2 specifically for the U.S. regions across the on the horizontal axis is all of the grid subregions across the United States, and the vertical axis is the pounds of CO2 per megawatt hour produced. And to compare that is the green line is one of our model J420 gensets running on natural gas in a CHP application. So you can see the CO2 emissions is considerably lower than the majority of the other, really what was typical in each of those regions. There's one or two others, 1, 2, 3, 4 regions that are lower than the 420, but the majority are considerably higher. And using an example of a municipality, in this case, we're looking at 3 generator stations with a total output of 22 megawatts. The 3 kind of breakdowns is 14.5 megawatts of older type of generation with 3 megawatts as base load and 4.5 megawatts as peaking plant operation, totaling up to 22 megawatts, averaging, again, as what one of the earlier slides showed, of 36% efficiency. In this case, we're comparing that to a typical recip engine in a CHP mode. In this case, is greater than 90% efficiency. On the far right is the green portions, which is, again, one of our model J420 units in comparison to other technologies. The only one for CO2 emissions that is less is actually a fuel cell, which has no emissions. Every other type of technology for generation is considerably higher. And then with NOx emissions, there's only 2 that are lower, the fuel cell again, and then a combustion turbine. So again, it's showing that recip engines in a CHP application can significantly cut down greenhouse gas emissions and lower emissions overall. Moving into the economics of CHP. When you're looking at a project and considering CHP, there's a number of things you really need to consider up front. I kind of use this as kind of a checklist when I'm talking with someone. If a developer or someone calls me and is interested in CHP, I said, well, let's talk about what you have there and what you're thinking about. The first, and I'm just going to go down these bullet points. Is it CHP or is it going to be trigeneration? Trigeneration being electricity and thermal energy, but also cooling derived from the heat coming off of the engine. So that's the tri and the trigeneration. What are your current electricity and gas costs? What is it costing you to purchase electricity from your local utility, and what is it costing you to purchase gas from your local utility? Is the system you're looking at going to be operated in a grid parallel or in an island type operation? Grid parallel meaning that it's going to be running parallel to the grid, and it will be running all that time using the grid as a reference, as well as combining those 2 streams of electricity to feed all the downstream loads. Island operation would be isolated from the grid and operate independently of the grid. It's not necessarily that the grid is not there, but it's just not connected to the grid. The 4th bullet is about electrical and thermal load curves. Have you taken the time, if it's an existing facility, or even if it's a planned facility, have you taken the time to plot out what you think the electrical load and thermal loads are going to be, or if it's an existing facility, what they actually are? Ideally, your electrical and thermal loads will run through peaks and levels at the same time, so they run concurrent to each other. If not, sometimes you can shift one of those. You can go through some operational things, and this is can be quite complex to figure out how to shift loads so that they do run at the same time, so that they're synchronized. Another item that to really be considered is the CHP project that you're looking at. Is it going to be part of a new construction project, or is it going to be added to an existing building? If it's new construction, that's probably, I'm going to say that's the better of the 2, because you're starting somewhat with a clean sheet of paper, and you can choose the best, i.e. most efficient place where to physically locate your equipment, as well as where to tap into your electric systems and thermal energy systems, whether it's hot water, or low pressure steam. If it's an existing building, that may really bring some constraints to you as to where you can physically locate equipment, and also where you can tap into those existing systems in your building's infrastructure. So that may restrict you a little bit, and you may realize a little bit lower efficiencies because of that. But it's important to look at that up front during your initial design phase. Moving into some more of the cost aspects, CapEx, capital expenses. This is really what it's called. These are your upfront costs, and they consist of the CHP equipment costs, the genset, the balance of plant, any type of paralleling switchgear, anything that allows you to put together a functioning CHP system. Next set of costs is what will it cost you to interconnect with the electricity and gas utilities. This can be relatively simple, or it can be very complex and quite costly, because in some cases the existing utility systems, whether it's the gas pipeline or whether it's the electrical distribution center system, may not have the capacity, and as a result it will have to be enlarged or modified in some fashion to accept your CHP system, and those costs would fall upon you to cover. And the next item would be investment incentives and grants. These could come in either federal, state, or local systems providing investment incentives, and in some cases flat out grants. And I'll show an example. One of our case studies, I'll show you an example of that. O&M, operations and maintenance. Fuel costs, obviously, you're going to be burning fuel, so you need to know that. Consumable costs, these would be filters, lube oil, spark plugs, anything that's consumed during normal operations. Scheduled maintenance costs, these would include such things as valve adjustments and other types of things that may not in addition to the consumable cost. And then equipment depreciation, this would be basically really from your CFO determining how rapidly do you want to depreciate your equipment. And that would play into how you're going to work your budgeting figures and so forth with your design. Cost savings to be taken account of are the reduced purchase electricity. Since you're generating electricity, you're going to be using less of it. However, you are going to be using additional fuel costs, additional gas, but you're going to have reduced gas heating costs, if you can follow that. So if you have an existing boiler system, you're going to be using that system less, but you're going to increase the gas usage for your CHP system. And then if this is available, revenue from the export of surplus electricity. If you're generating more electricity than what your project load is, you have the option, if you can get into a contractual agreement with the electricity utility in order they will purchase that export power from you. And then there's also revenue from operational incentives, much like the investment incentives above. Some utilities and other groups will actually make available to you operational incentives once you're up and running. So these things all need to be taken into account for the economic analysis. This is really just kind of a visual which kind of explains some of the things I talked about in the previous slide. So I'm going to go by here quickly. Now we're going to look at 3 case studies about CHP. One's fairly new, 2 are older units, so we've got some good data on these. The first is a case study it's a hospital in Puerto Rico, and as we've probably known over the years, Puerto Rico does not have the most robust electrical grid there. So in this case, this is a hospital, general and surgical type hospital, with an average load of 1,200 kW, and the primary purpose for putting in the CHP system was for energy savings and resiliency, so that they're not dependent on the grid. The solution for this situation was actually consisted of 2 of our model J420 units and arranged in an N+1 configuration. And actually in this case, it's really a 2N configuration, since there's only one engine has to run at a time to satisfy the load. So the other is there as a backup. And when the first or primary unit is down for planned maintenance or for any other reason, the other one can come online and carry the load. So the hospital is never without one of those engines available. The fuel choice on this one was propane due to the lack of a natural gas grid in Puerto Rico, or at least not to this site. So they chose to use propane. Again, this is a 100% islanded mode, so it was completely independent of the grid. Average load was 1,200 kW, and it's been in operation for 4 years now. And the benefit to the hospital was that the hospital stayed online and powered by this unit during and after Hurricane Maria. So the quote at the bottom is from an NPR story about the critical needs of hospitals in Puerto Rico, and the quote reads, "We had good emergency preparedness plans that we put in place. We produce our own electricity on site, and also it is more reliable since we don't have electric lines, transmission lines, and all the losses that you have in a regular system from the utility grid." So again, this is a good application and good results over a number of years from CHP. The second case study is another hospital. This one is in the U.S., and the CHP portion of this particular project is a natural gas 2 megawatt continuous CHP system. It operates in 2 modes. The first mode is run normally parallel to the utility. There's multiple utility feeders coming into this hospital, so it's normally running parallel to them. Excuse me. However, if the utility does go down for whatever reason, the standby generators come up to speed, and then the CHP operates in parallel with the standby generators. This is a little different than what's normally seen, but it was very important to the customer that the CHP operate as much as possible. It also, by using natural gas, it diversifies their energy supply. So they're using electricity plus the natural gas pipeline, which was readily available in the area. And it adds non-critical emergency electrical capacity to them. The benefits to the hospital: improved resilience. So the assets, meaning all of their operating units and so forth, they stay online even during outages. Energy savings to them is approximately $760,000 per year. Reduced emissions, as we talked about before. Upgraded their infrastructure by improving their boiler and chiller systems by using the CHP as a supplemental source. And the reduced upfront costs. They took advantage of the investment incentives and grants and so forth. And I'm going to actually share with you some of the financials for this particular project. The cost of the system overall, the addition of the system to the hospital was approximately $4 million. The incentives and grants, the utility provided them with a $2.1 million incentive. State energy program provided them an additional $500,000. So really we're looking at $2.6 million right there against a $4 million installation. Annual savings broken down as electrical utility cost savings of $1.25 million. Yes, they are using a little bit more gas, so that they're using $485,000 worth of additional gas. Using an estimate, and this is a very conservative figure, of 75 to 80% total CHP system efficiency versus 35% for the utility power, they're realizing, or they're expecting to realize, a simple payback period of 1.8 years. So that's a pretty quick payback period for a $4 million system. And one of the reasons this particular hospital went with CHP is they have experience at multiple other hospitals with CHP. So they've had very good experience with them. So they've chosen to do CHP on their hospitals. In fact, they're very interested in putting some into their existing hospitals. The third case is a food processing facility. This uses a single 1 megawatt, one of our model J320 gensets, using biogas, which is produced by an on-site anaerobic digester. So really what we're doing is waste products from the processing are put in the lagoon, run through an anaerobic digester, and produces biogas, which is then run through the engine, which produces electricity and hot water for the processes there at the facility. They're also able, in this particular case, to sell the renewable energy credits. So that's another revenue stream for them in this case. The benefits to the facility are improved resilience. So it's really, this 1 megawatt engine is covering approximately 20% of their total power there at the facility. They're realizing $900,000 a year in savings. And this is based on their actual cost and an 82% total system efficiency. Emissions have been reduced 52,000 tons a year of carbon dioxide emissions. And kind of an extra is that they're by putting the waste in the lagoon, they're not actually having to transport that waste away and having to pay tipping costs. And because of all this, they're able to realize a 1.5-year payback period. So those are the 3 case studies I wanted to share with you. Now we're kind of going to go into a process. Now I'm going to go through this relatively quickly. With Jenbacher's experience, with over 8,300 gas engines installed, we're prepared to offer the following services, really a feasibility study. Christian mentioned this earlier, a feasibility study which really helps identify the on-site power generation strategy and, really to deliver enhanced efficiency and cost savings. Moving forward into the process of a project, we're looking at the design and development, detailed cogeneration engineering and equipment, as well as the CHP sourcing of that equipment and cost benefits analysis. Again, this is both for outside customers and inside if you need to really to sell a project inside your company. We can assist you with that. Delivery and installation is complete project management, including delivery and installation of the equipment and coordination with the local utilities. This last item, the local utilities, as I mentioned earlier, can really be a real resource hog. It can suck up a lot of time and slow the project progress considerably. And then the maintenance plan, just a brief description here, is a maintenance schedule. I'm actually going to elaborate a bit on this on the next slide. Maintenance plans, we're looking at multi-year agreements, or MYAs as we refer to them. And they consist of several different components and options. Starting at the lower left, we're looking at remote monitoring. This is a 24-hour, 7-day-a-week hotline with remote monitoring of the generator operation and call-out guarantees. Material stream agreements. These will be predetermined parts kits, spare parts, and volume frameworks. The CSA, or preventive CSA portion for our services, would include scheduled maintenance and on-site support. So this would all be arranged ahead of time. And the corrective CSA is the preventive CSA for unplanned repairs, troubleshooting, and performance guarantees. And then at the last item up shown here is the value-added options. These will be major overhauls. As your equipment really accumulates a lot of operating hours, at a certain point, overhauls are going to have to be required to maintain the equipment, and also upgrades of that equipment, so that you're always going to be upgraded to the latest technology available for that particular model. So it's not going to be obsolete as soon as you take delivery of it. It will be available to be upgraded. This is kind of going into a little bit more information on it. Again, it's kind of some of the same topics I mentioned on the previous slide are covered here. Particularly, one thing I want to stress is, even though we are a worldwide company, we do have local service technicians across North America. And I just wanted to bring to your attention, this is the first of 7 webinars. 6 are focused on CHP and its specific application. The last one on December 7th is actually more of a service-oriented, or service-focused, I should say, webinar about Jenbacher gas engines and particular types of oils that are available. So today being Wednesday, the 20th of October, the first 6 are the next 5 that are shown are going to be every week, every Wednesday at the same time, with the exception of Thanksgiving week. We're going to skip that because most of you, well, I shouldn't say most of you, a lot of you may be on vacation or doing something else. It's a short week anyway. So we decided to skip that week. So between now and December 1st, every Wednesday, I want you to put on your calendars that at this time, you're going to join us for the next webinar. And these are the topics you see: the microgrids, hydrogen, and data centers and critical facilities, food and beverage focus, water including wastewater treatment, and the last would be the greenhouses and grow houses. And this just shows quickly, just shows the area of North America and where our locations are. The green being our direct business with which Christian and I both belong. And then we have distribution color-coded here on the legend that you see. So we're now ready for our questions and answers. I have been seeing lots of questions coming in, so that's very positive. I like to see that.
Super. Well, thank you, Gary and Christian, for your presentations, and thanks to all of the attendees for your attention. As Gary said, we're now going to move into the Q&A session, and if you still have questions, there's plenty of time to enter them in the widget. Before we begin the Q&A, I would like to once again ask you to complete our survey, which is found in the widget bar at the bottom of your screen, and this just will let us know how you're finding the webinar so far. If you would like us to get in touch with you right away, there are a number of ways to do so. You can let us know in the chat via the Contact Us widget on your screen right now, or you can fill out a form at either www.jenbacher.com/America or www.INNIO.com. So let's get into some questions and answers. Let's start with this one. How much downtime is required per day, month, or year? Can these engines be run continuously? Christian?
Yeah,
Gary?
I can take that. Yes,
please.
the engines are designed for continuous operation 24/7 at 100% load. So all the downtime you would typically have is for preventative maintenance, which typically is somewhere between 2,000 to 3,000 hours as the shortest intervals. So that might include spark plugs, oil changes, and so forth. But generally speaking, they run continuously and only have very minimal preventative maintenance, which is typical for obviously gas engines running.
Thanks very much, Christian. The next question is, I've seen setups in the Philippines that use Jenbacher gas engine firing biogas. Do you have existing projects that run on syngas from pyrolyzer or gasifiers?
Yes, we certainly do. Jenbacher is one of the pioneers, really, of non-natural gases, which obviously include biogas. But also on the syngas side, what sets us apart from others is our experience on syngases, which typically contain hydrogen, carbon monoxide, and other like non-typical combustible fuels. So yes, we have a lot of installations running on wood gas, on other syngases, coke oven gases. So pretty much any gas that can burn an engine, we probably have running somewhere in the world. In all cases, we always ask for a gas sample, an analysis showing the composition, and then we'll evaluate which engine fits for that application. But yes, we have a lot of experience on syngases.
Thanks again, Christian. There's a few questions asking more or less the same thing. If there will be a replay of today's presentation or if it's be accessible after this webinar, the answer is yes. There will be an on-demand version of this webinar available for you to listen to at your chosen time, beginning this evening, latest tomorrow, and you can simply visit the same platform that you did to join today's webinar and be able to replay the webinar again. Moving into a different question. Here's a question. Are you able to share any success stories for wastewater treatment plants? Gary and Christian, unless you want to answer here, I think this is a topic for one of our upcoming webinars.
And that's exactly what I was going to say. That is, and that question was probably asked before we got to the webinar list. But yes, that's going to be the focus of one of our upcoming webinars about water, which will include wastewater treatment plant and case studies.
Yeah, that's right. And that webinar is scheduled for the 17th of November. So if the person who asked the question would like to sign up for that webinar, you can find all the information on INNIO.com or Jenbacher.com/Americas. Let's see, moving to another question. Your gas to electric spread graph ended in 2016. How are current elevated natural gas prices affecting CHP economic viability?
They are affecting it because, I mean, obviously that's clearly one of the factors is the cost of fuel versus the cost of electricity. So yes, there is. And in fact, about 15 years ago, it was before deregulated electricity and, I'll say artificially low electricity, and natural gas was very high. It did not make economic sense to do it. So there had to be some other overriding factor, whether it was resilience or something, or sustainability, or something along that line that overpowered. But taken strictly on dollars and cents, no, it did not make sense. And we have seen recently an increase in natural gas prices. The long-term forecast, what I'm seeing though, is that natural gases will stay low relative to other fuel sources for quite a while. I haven't seen any end to it, but yes, it does kind of narrow it down. It may stretch out your payback period a little bit, but you also have to take that. That's just one factor: high fuel costs. The other factor is, again, electricity, and the other issues are the other economics that I mentioned in the couple of slides talking about the economics of CHP.
Great, thanks, Gary. Here's a question. I'll paraphrase. Do you have support or activities in Hawaii?
Yes. So in Hawaii, our Western area distributor, Western Energy System, part of the Penn Power Group, has a representation there, and we also have some Jenbachers running at a hotel there in Waikiki, in Honolulu. So yes, we have some presence there. The challenge in Hawaii is really the gas availability. So it's to some extent available in Honolulu and the surrounding areas. They have a little bit of an off gas there, including some hydrogen in it. But obviously on the smaller islands, it's mostly propane, and propane comes at a relatively high cost. But that's also a possibility as a fuel in our engines, and we also have engines running on propane. So yes, Hawaii is an interesting market, especially due to the high cost of electricity there.
Yeah, and that's going to be similar in other large islands too. The availability of some kind of a gas storage or transmission, and also again the economics of the gas versus the electricity that's available.
Excellent, thank you. The next question is, how close can a container with a 2 megawatt gas engine power plant be located to residential buildings?
So that's always a quandary, particularly if you're talking about hospitals or things like that, which tend to be close to residential areas, and that's really going to be site specific. There's going to be regulations based on the local officials, how much whatever the decibel rating at the site would be, or at the property line. But yes, you can put them close. I've put a CHP right next to an apartment complex. Within, I think it was less than 80 feet away from the nearest edge of the CHP enclosure to the apartment, the closest apartment balcony. It can be done. It's just a matter of if it's a containerized unit, it's a matter of getting the sound levels, the sound attenuation of the container sufficient to meet the requirements. So yeah, it's hard to say you can do it by so many feet, but again, it's very site specific.
Okay, here's another product related question. What NOx emissions intensity is typically achievable with Jenbacher cogeneration units, assuming all heat is used? That is, without the use of add-on emissions controls such as SCR.
So there's really two standard emission levels on natural gas. One would be 1 gram per brake horsepower hour, which is the defined emission limit by the EPA. And the other would be a half gram, 0.5 grams per brake horsepower hour, which would be typical, let's say, in the Northeast in some areas there. And if you go below that, you would use an SCR to get lesser NOx emission levels. So typically how we approach it, we look at it from, obviously an EPA level, a state level, a site level, what's the total amount of emissions which are being generated at the site, from other emission sources, boilers, and so forth. So we always look at the holistic picture of, from federal to state to local requirements, and then come up with the best option for the engine, and size any needed after treatment as well.
Thank you, Christian. Here's an additional question. I'll paraphrase. What is the maximum capacity available of your engines in megawatts?
Okay. For single units, our range runs, and this will be, I'm going to use nominal sizes, between 300 kilowatts and 4.4 megawatts in a single unit.
And to add to that, there is also a 9 megawatt solution, which is occasionally used for larger utilities type projects, but typically for CHP projects, which we see here in the United States or in North America, we typically go as high as 4.5 megawatts in a single unit, and use multiples of those then if needed.
Okay, thank you. Where are these units fabricated, and what is the typical wait time to receive a unit?
The units are built, the engines, or engine generator sets, let's say, are manufactured in Jenbach. That's our headquarters in Austria. From there, they either get shipped directly to the site where they're integrated into a building, or we also have options to package them in containers, so that you have containerized outdoor enclosure types products. Those packagings are also done in Europe, so we also then ship the complete containerized system to North America and do assembly at site. Generally speaking, the wait time or the lead time, depending on the scope, on smaller engines, just the bare engine, somewhere from about 20 weeks, and it goes up to about 40 weeks on the very large engines or more complicated packages. So there's a wide range really of lead times depending on the size of engine, the type of packaging, the type of scope. So, anywhere from maybe 5 to 8 months, roundabouts.
Okay, thank you. A question regarding financing. Does Jenbacher offer financing options? And if so, how would I go about starting that conversation?
No, we do not offer financing. If you've been in the business a while, in one of our previous iterations, we did have a financial arm that is no longer available to us as INNIO Jenbacher.
Going further, do you have partners in Canada for CHP projects?
Yes, we have. Canada is covered by one of our distribution partners. If you can see the map now, it's one of our partner there is Interflex. So they cover all of Canada.
Excellent. And still have quite a few questions. No mention of use of battery storage on any of your successful case studies? Question mark. Was it not required?
The case studies that I shared with you on this one are a little bit older case studies. The most recent one is probably about a year old. So at that time, during the design and construction and installation and operation, stored energy had not yet really come to, hadn't come to fruition. We are currently working on projects that do have stored energy as a component in the overall system. And that's really one of the applications we're seeing a lot of opportunities on is gas engines being used not only with stored energy, but also renewable energy as a key, with the gas engine being a key component. It may be the last technology that's turned on, but it's always there, and it's available. And when the wind stops blowing, or the sun's not shining high enough, or the batteries are not quite able to provide full power for a full length of time, the gas engines are there as a reliable backup. But yes, I think in the future we're definitely going to have some case studies that will have stored energy. Okay,
thank you. Here's a question in regards to overhauls. Once the engine reaches the time for a major overhaul, is it performed on site by INNIO, INNIO Jenbacher, or distributors? Can you explain your engine swap program?
So the engine overhaul at the end of the life of the engine is done through swapping it out through a remanufactured, rebuilt engine. So the overhaul is not done at site, at least not in the range of the up to 4.5 megawatts. So basically, a new engine comes in, you swap out the old one. Takes 1 to 2 weeks, let's just say, broadly speaking. So it's relatively quick. That's done either through our Jenbacher directly, or through our service partners, depending on where the location of the site is. But it really aims at keeping the downtime minimal that you put in a new block, and that new block then is good for the life of another life of the engine. So it's basically like a new engine in terms of performance.
Okay, thank you, Christian. Here is a question, and I hope I'm understanding correctly. It's in regards to adsorption chillers or absorption chillers in the CHP process. Can we answer this one?
We have used absorption chillers in the past. Adsorption, I'm not sure of. Christian, are you familiar?
No, it's absorption with the B. So right. Yes, that's done. There's different configurations available using the engine cooling water, the exhaust, or both. So it's a fairly proven technology if there is a large, cooling need there at the site. So I would say it's still more common to use hot water or steam, generally speaking, in CHP applications here in North America. But absorption chilling is used, and it's also a proven technology.
Okay, I think we can maybe have one more question here. The question is, how much wood chip volume would it take per day for a 1 megawatt system for a strictly biomass operation?
That's a good question, which we'll have to defer to our engineering. I know sometimes we get questions like, how many cows does it take to power a 1 megawatt biogas, or I guess now how many wood chips? And it's a fair question.
Yeah.
But that's not something I can give you a ballpark number here on the fly.
I was going to say, I was chuckling because neither can I. Yeah, the number of cows is one thing, but the wood chips is, that's something I'm not familiar enough with to have a rule of thumb available.
That may be one we need to get back via email on.
Yeah, exactly.
So let's see, maybe one final one. Again, paraphrasing, I believe the question is, what is the typical life of a Jenbacher gas engine before needing a rebuild? I think this is about operating hours.
Between 60 to 80,000 hours, depending on the model, depending on the fuel, and other factors. Between 60 to 80,000 is as we call it, the TBO, time before overhaul.
Perfect. We are running out of time, and we're right at an hour. Thank you for everyone who has asked questions. There's several that we unfortunately will not be able to get to today, but as we mentioned earlier, we will come back to you via email. Thank you very much for everyone who did submit questions, and those who requested to be contacted. We will do so as soon as we can. We've reached almost the end of today's webinar. Please remember that today's presentation is available on demand, so feel free to visit the platform and listen again if you'd like. You can also share today's webinar with others. On behalf of Gary and Christian and Jenbacher North America, thank you for joining today's webinar on CHP. We hope you found it interesting, and we look forward to speaking with you about how Jenbacher gas engines can support your CHP project soon. With that, I will close the webinar. Thank you very much, and have a nice day.